In this session, we are going to review the main concepts of a graphical information system, that is an acronym indicated by the letters GIS, and digital elevation models focus on the use of the hydrobid flood model. The presentation consists of three parts. The first part is a review of the basic concepts used in GIS. The second part, we're going to review some formats of spatial representation of information. And the third part will be dedicated to surface terrain modeling. We're going to start with the basics of GIS, emphasizing the aspects that must be taken into account when using the hydrobid flood under the graphical user interface that we use with QGIS. The term GIS comes from the acronym, as I said before, of Geographic Information System. It is defined as a set of methods, tools, and data that are designed to act in a coordinated and logical way to capture, store, analyze, transform, and present geographic information and its attributes for multiple purposes. GIS technology allows you to handle and analyze spatial information. It originated as a result of the need to assess information, to solve problems and answer questions in a rapid way. As depicted in the diagram, a geographic information system is not limited to software, which is only one of the components. It also requires a hardware, that is a computer system, either for acquisition, storage, and processing of the information, data that will be or will characterize or define the system, analysis, that is a process that will help understanding the algorithm to be applied to the data, and finally, and probably the most important part, is the people who are in charge of assembling all the elements to implement the geographic information system. A geographic information system is implemented by making the abstraction in which the elements or components of a system are represented by georeference spatial information layers. For example, if the system to be modeled is a hydrographic basin or a watershed, the model could contain a layer with the terrain elevations, another layer that will represent the soil units, another layer that would have the vegetation cover and land use units, another layer for the drainage network, and so on and so forth. In this way, you could have all the elements required to perform simulations in a watershed system. The information is not limited to spatial geographic data, but layers have alphanumeric information known as layer attributes. Each layer has a corresponding attribute table. In the attribute table, each record or row corresponds to geographic elements, either a point, a line, or a polygon. These are the three main geometric elements that we are going to be using in the hydrobid flood model. Later, we will see that there are other layer formats where the relationship is one-to-many and not necessarily one-to-one. That means that one geometric element does not necessarily have one relationship with another one, but it has with many other parameters. The attribute table is a fundamental part of the layer, and it contains the fields in columns with the information associated with each geometric element. In general, there will be a field with an identifier which will allow anchoring or linking the alphanumeric record to the geographic element. That means that the geographic element will have the corresponding attribute or attributes. This identifier can be a code, a name, or simply a serial. A geographic information system works like a geospatial database. Its first function is to store information in a structured way. The main use given to geographical information system is the manipulation of spatial layers, mainly analysis of layering and the relationship between the layers. It also allows quick retrieval or consultation of both spatial and alphanumeric data. Also, being a database, you can establish a relationship between the attribute tables of the different layers and form an information system through which analysis and queries can be made beyond a simple spatial association. Spatial queries do not require that the layers be related through their attribute tables, but rather that they share the same geographic space and that they be georeferenced using the same coordinate reference system. This is very important, and we'll talk about this later also. It is important that all the layers keep the same georeferencing system in order that they can relate to each other in a correct way. One processing technique is to acquire the attributes of a given attribute of elements in a layer that overlap another layer. So let's say you have one layer and you want to get a value from a different layer, so they need to be in the same coordinate system. This technique is used, for example, in hydrobid flood to sample or to acquire the elevation on the mesh cells, as we will see, from a digital elevation model. So the cells that the model will use to compute velocities of flow, the depth of flow, will need to have a bed elevation or a bottom elevation. This bottom elevation will be sampled from a different layer that will be will be a digital elevation model. Also, within the same layer, the elements adjacent to a particular element can be obtained. Another geoprocessing technique is to select by overlapping the elements of a layer that intersect with another. An example of this in the hydrobid flood is when a cross-section is created. The line that defines a cross-section is superimposed on the layer of the mesh and selects the cells intercepted by that line. This is important. We will see this practically, but you will be able to select a cross-section and extract the model results from that cross-section. And that is a very useful tool to analyze your modeling results. GIS software has tools to generate the final products that can be used in a report, such as maps that can be composed with different layers that contain typical elements such as scale, legend, and of course the results of the model. As you can see here in this, you have the depth of flow, but at the same time you have the legend that indicates the color scale that corresponds to each depth range. And also you can have time and other titles within the map. You can have reports, and this report can contain the numeric values of the different, for instance, depth at different locations. And you can generate graphics of all sorts as well. The capability of a graphical information system to model systems such as a watershed is, in reality, is very limited. because the actual purpose, as we mentioned, of a graphical information system is not necessarily to model, but to represent the geographic information that you can represent in the database. And for that reason, it's not natural to make such simulations like rainfall runoff or something for hydraulic nadir. And for that reason, the geographical information systems need to be associated with a mathematical model that can perform such simulations. So in such a way, the models perform the computations and interact with the geographical information system to store and prepare all the necessary data. And the results of the model are later represented in map form or in graphic form, such as hazard mapping or depth and so forth. Given the capabilities of a graphical information system, these have become a natural platform of graphical user interfaces that allow to store and process the information required by the mathematical models in a way that can be automated in a more user-friendly way. GIS also allows post-processing of the results generated by the models in animations and many other forms that we will see during the course, which generally are text files that are difficult to read. So normally that's the results of the model are text files, are not graphics. So the graphical information system is able to read these files, process them in the graphical information database, and then generate the graphs that we are much simpler to analyze and interpret in this way. As you can see here, this is the cross sections I was referring to before, and you can see that in the river that appears in the upper part of the window, you can see a red line that is the cross section. Then on the bottom, you see the actual cross section with the discharge or flow rate that passes through that cross section at a given time. Now we're going to focus on the formats in which geographical information system represents the spatial information. Geographical information systems represents spatial information using basically two models or formats. These are vector format and raster format, or vector models and raster models. Each model has its advantages and disadvantages, and we are going to be using both of them for different purposes within the hydrobid flood system. The vector format is more applicable to when you want to represent discrete information or let's say lines or polygons or attributes associated to lines, points, or polygons, while the raster format is better suited to represent continuous information like surfaces or that type of data. The fundamental unit in the cases of a vector model is the point or node, but then the node can relate to other nodes to form a line, and then the lines can relate to other lines to form a polygon. And again, as everything geographic objects in the GIS environment is related to alphanumeric data, then each of these objects can have its own attributes. And that's the basis of the vector model. In the raster model, each point has an information that can be an elevation or a value or a result. It can be the depth of flow, or it can be the elevation of the terrain, or any other useful information that you want to store in that way. So the vector model is based on three basic building blocks. So you have first the node, as I mentioned, that is the basic unit that represents all the different entities. Then you have the line or polyline, and this polyline can have any number of nodes. Then you have the polygon, or the areas that is used to represent two-dimensional entities or two-dimensional geometries, as you see on the figure on the right. Between them, there is a series of relationships so that a line can be defined by two or more points, and then the same thing applies to the other geometries here. So the vector model, as I mentioned, has geometric attributes. One of the advantages of the vector model is that the spatial elements have associated attributes. And this relationship can be one-to-one. So one spatial attribute corresponds to one record, or many-to-one. That means that several spatial objects can have one record. The attributes are stored on a table where the internal identifier associates an element or several spatial elements to a record in the table. So if you want, for instance, associate one point to one depth, that's a valid thing. But for instance, you can associate one spatial element to many records as well. So it depends on the applications you are dealing with. The vector format allows establishing relationship between the elements of the same layer and also between elements of different layers. So you do not necessarily need to restrict yourself to relationship on a one layer, but you can make connections and relationships and even calculations between values or objects of different layers. The topological relationships allows you to establish the connectivity between the elements of the same layer. For instance, we could establish the order of channels in a layer that represents the drainage or channel network. And this type of relationship relies on attribute data. Spatial relationships are those that are established between layers that occupy the same geospatial extension. And these relationships are determined through superposition, intersection, among others. These spatial relationships are one of the most powerful capabilities of geographical information systems, and they facilitate the extraction of important information contained in the layers. These tools are extensively used in the data generation phase of the hydrobid flood model, as we will see in the practical sessions that we're going to go through the course. One aspect to keep in mind with vector layers is whether they are simple geometries or multi-part geometries, as they are called in QGIS. Simple geometry objects are those where the relationship between the number of spatial elements and records in the attribute table is one-to-one. This corresponds to the image on the right, where you see that we have 5 geometric elements that are colored in the figure, and there are also 5 records in the attribute table, are on the table below. On the other hand, that you can see on the left, the multi-part geometry is where one record or one of the records in the attribute table corresponds to more than one spatial element, as would be the case on the, for instance, the red image, the red polygons, and also the blue ones. The blue one corresponds to one element on the table, one record on the table, and also the red one. So you can mix and match different geometries on the same layer. In general, the hydrobid flood model can work with multi-parts geometries. However, not all QGIS plugins, different from the one that we use in developed for hydrobid flood, work well with this type of multi-element geometries, multi-part geometries. So it is recommended to work with simple geometries as much as possible to avoid problems with other of the plugins that are available to use in the QGIS system. Now, the raster model is very different from the vector model in the sense that the information is represented as a discretized set of regular cells that can be square and also rectangular. Most of the time they're square, as you can see in the figure there. Each of these cells contain a number that can be the identifier or the value. The model does not necessarily have an attribute table associated with each cell or each pixel, as it is the case of the vector model. We should not confuse the raster model with a grid, which is a vector layer that emulates a raster, and therefore it has an attribute table. And remember, in the raster model, there is no attribute table. The spatial extent of a raster is determined by the coordinates of the upper left vertex of the raster, the size of the cell, that, as mentioned, can be square or rectangular, and the number of rows and columns. So it's a very simple way to store information, and it's very practical as well to share mainly terrain information and also modeling results, as you can see in the image. Other important characteristic of the raster model that must be taken into account when doing operation or processing raster layers is that there is often a value that is called a no data value that is used to define cells or pixels on the raster that do not contain any data. When a raster is created using QGIS, by default, the no data value is assigned a -9999. That's the default in QGIS. However, you have to keep in mind that some other plugins and some other software, that value may change. As you can see in ArcGIS, for instance, is -32768. It's very important to keep this parameter in mind when we use raster from different sources, generated with other software or generated with other sources, because you may expect some weird results if you are using a no data value different from the one that the original data file was preparing. Another important parameter to consider is the type of bit used to implement a raster file, and this bit is the way that the raster uses, or is a parameter by which the raster uses to store more information. The range of values that the cell can store will depend on this parameter. For instance, if the file is an 8-bit file, the range of values will be between 0 and 255, which is very limited in a sense, but there are many data that can be stored using by bit in any case. And for instance, when you have 16-bit, for instance, the range is from 0 to 65,535, so 65,535 values, and so forth. So the memory size that the file will occupy will depend also on the type of bit that is used. Therefore, it is good to keep in mind that the type of information that will be represented or stored in the raster at the moment that the bit type is selected, if you are creating this for the first time, of course. If you are just importing a file with the terrain, for instance, that is already embedded in the file you're reading. If the layer is used to represent land use units, for instance, where the number of units at most would be about 10, an 8-bit file would serve that purpose very well. On the other hand, if the file is used to represent a digital elevation model, it would be much better to work with a 32-bit file. This parameter should be considered when using raster generated in other software systems, since some processes may fail when layers of different byte type are being operated, and some QGIS plugins only work with certain type of these formats. Another characteristic of the raster file is that they can be either monoband or multi-band. The files that are usually processed and generated by the hydrobid flood are monoband. They contain a single layer. There are also raster files that are packed with several layers or bands, generally 3. The typical example is a multi-spectral images or of satellite images, where each layer can represent a range of spectrum of light, so that we will have a layer or band for the red color, another for the green color, and another for the blue. Combining this information can depict a true color image that also applies to color image files such as photographs. So these are typically multi-spectral, multi-band layers. Among the processing capabilities offered by the raster model is the possibility of doing algebraic operations between the layers. We can do this using the raster calculator or applying a Python script. Python is a computer language that you can program in that computer language within the QGIS system. It's a very powerful language that allows you to extend the capabilities of the QGIS system, as we will see. It's very important to understand that the Hydrobid flood plugin was developed using the Python language, and all the code of the Hydrobid flood plugin to handle all the data, preparation of the data, and also post-processing is included in the installation that you have. A typical example of raster calculation would be to compute the soil loss using the USLAE equation, for instance, using a different layer to represent the variables of the equation for C, K, LS, and P, and then doing the multiplication layer by layer as if it were variables. So this means that you have a large potential here, as you get more acquainted with the system, to make computations and embed this computation in scripts. Another example is, for instance, it's very common in hydraulics and also in river analysis, is the volume calculation. This type of analysis allows computing the volume between two different raster layers and calculate the volumes in between these two surfaces. For instance, assume you are using the hydrobid model as a sediment transport model. So you're analyzing a river and you want to know the erosion and deposition volumes that occur in the river. So you want to know if the river is degrading or is aggrading. You can use this tool to have, let's say, the bed surface of the terrain that it was before the sediment transport simulation, then the surface that ended after the simulation of sediment transport. And the difference between these two surfaces will give you the surface like it is here on the right, where you have areas of erosion, like with the minus values here, or net deposition. It's very useful to understand which are the more critical areas in this type of analysis. But you can use it not only for sediment transport and erosion deposition areas, but also for other purposes as well. Another application to raster cell statistics is when it is superimposed with a vector layer, which allows obtaining the average or mean, maximum, minimum values of the cells for each polygon of the vector layer. This application is very useful when characterizing hydrological basins by superimposing, for instance, the basin layer on a raster that represents the slope values. So it is possible to obtain the statistics of this variable for each basin, maximum, slope, etc. Another useful tool that sometimes you may want to explore in the future is reclassification. It's a geoprocess by which the original values of the cells are classified or reclassified in new categories of different integer values that may have. Sometimes this is used to replace values with new information, to create groups with similar values, to reclassify values on a common scale, or to assign certain values with no data values, as I mentioned before. So there are many potential applications of this reclassification in the hydrobid flood system. These figures try to summarize or compare the different formats we have been looking at, the vectorial vector format or the raster format. You can see here that the representation of the vector model is more accurate. You have the exact, for instance, if you wanted to show streets or a lake unit or some areas that represents parcels of land or something like that, it will be much more accurate. While the raster model, in order to increase the accuracy, you will need to decrease the size of the cells very much in order to capture this type of situation. However, if you want to capture a terrain and the variability of the terrain, the raster model will be much better suited to that end than the vector model. So you have advantages and disadvantages of each type of representation. In summary, the vector representation is based on points defined by x and y coordinates. These points can be joined to form lines or polylines and eventually polygons. And it should be noted that the shapefile format that I haven't talked about that, but we'll make use of that extensively during the course. The shapefile format is the native format for the vector layers. Shapefiles were generated by, designed by ESRI many years ago, and they're still used. It's a binary format that store both the geometric elements and also their attributes in a set of files. I would suggest that it is the most common vector interchange format. It's very standardized, and it's used in hydrobid flood for many of the layers that we are going to be using. The raster representation is based on cells, as I mentioned, that are regular in size, and in the model we use raster cells that are formed by squares mainly. And the vector and raster model has also some differences related to topological associations. For instance, in the vector model, you only are allowed to have lines, polylines, or polygons. But the fact that you can have those allows you to make connections or relations. For instance, in the nodes, you can understand the node connectivity with other nodes, or the polylines, you can't analyze which is the left side or the right side of the polyline, depending on the direction you are traveling through that polyline. And in polygons, you can detect whether a given point is inside or outside. The only thing you can do in terms of topological associations with the raster model is the nearest neighbor, and it has some limitations as well. In geographical analysis, you can also, these geometric units, you can detect overlap, intersection. You can create buffer areas or buffer zones around each of these elements, and you can merge also or dissolve polygons. In the raster model, you can make different geographical analysis, but mostly they are related to paths that, for instance, if you have a terrain, you can detect the drainage network and things like that. In terms of mapping, and also summarizing the advantages and disadvantages, the vector model, it produces very accurate mapping with exact position, and it's useful for discrete phenomena and entities that have very precise edges or geometrical definition. In the case of raster model, it's more applicable to images also, or continuous phenomena that could be the rainfall distribution or the depth distribution or the velocity distribution and that type of thing. Okay, so now we're going to continue with the last part of the session, which is related to surface terrain model. And this relates to the way in which the terrain elevations can be represented in a geographical information system. A digital elevation model is the basic term that we will use to refer to a representation of the terrain. And this is very critical to what we are doing with the hydrobid flood modeling, because it is the basic information that we will require in order to make any simulation. The digital elevation model, or DEM, is the statistical representation of a continuous surface that in this case will be a terrain, and it's represented, it's constructed based on a set of points of x, y, z values, or a cloud of points that could be initially defined in an arbitrary coordinate system. The concept is more general, since the x-axis includes both the use of elevation, let's say the meters above sea level, and heights, that would be the topographic survey, as well as typical accidents in the landscape as river or ravines, or etc. For many users, the terrain includes both the planimetric and hypsometric elements typical of the landscape, as well as the information derived from the model, let's say slope, inner visibility, and orientation, among others. Now, very importantly, there are two main types of digital terrain models that we will be dealing with, and this is very important to understand. What is called the digital terrain model, or DTM, restrict the elevations defined in the digital elevation model to the actual terrain or land, and they ignore the vegetation and man-made structures. So they do not include trees or houses, buildings, bridges, etc. On the other hand, the digital surface models, or DSM, they do include the terrain as well, but also the vegetation and man-made structures. They would include trees and buildings, etc. It's very important to understand that, because in some situations, if you're dealing, for instance, with a rainfall runoff model, you want to use a digital terrain model instead of a surface model, because otherwise your model will think that the top of the trees that would be the ones represented in the digital surface model would be the ones where the water will flow. And that's not the case. We need the water to flow by the terrain and not by the top of the vegetation. So it's very important. We will come back to this in the practical exercises we're going to be doing. Now, the digital elevation model, they have the importance that they can be generated from contour lines or point values. So you can generate this in a wide variety of ways. There are many ways to generate a digital elevation model. And this is something that we will be doing in the course based on cloud, point cloud values XYZ, and also based on contour lines that represents lines of equal terrain elevation. Now, from the point of view of application, the DEM will be the basis from which a model is implemented using the hydrobid flood, because the elevation data is taken from the DEM and transferred to the calculation mesh. And then with this data from the mesh, the hydrobid flood system obtains the representation of the geometry of the study area. But in addition, from the DEM, you can also obtain other derivative values that can be useful for the effects of projects, such as shadow map, hillshade, as you see here, aspect, slope, and also contours. That is a very typical way to represent terrain areas. Now, how do we make a DEM? A DEM is obtained from the interpolation of discrete elevation data that can be obtained by direct methods. The classic way is by topographic survey, and but you can do many other ways. There are many other ways that have been developed. For instance, with the advent of satellites and aircraft flights, and also recently from the appearance of drones, now we have many accurate methods by which we can obtain data from the terrain and then create elevations, and that they include radar, they include GPA survey, and also LiDAR surveys. They can be done in many different accurate ways. There are also indirect methods, being the, for instance, the photographic restitution of, that is I would call the old ways of doing. It was a classical source of generating terrain elevations, and that's also possible to do it now. But also we can do even manual digitizing from paper maps that if you don't have any other data available. There are also public databases that are not sometimes very accurate, but they are databases that allow you to download DEMs online. Some of them are free. There are some that you can pay for, but they are sometimes a useful source of information for the DEMs. To build a DEM, it is necessary to perform an interpolation from the discrete data in order to have the elevation information continuously through the entire extension of the layer. There are many methods. Some of them are faster, some of them are more accurate, some of them are, it depends on the terrain that you have as well. And I will focus here on two of them that are the most used in what we're going to be working with river flow 2D and hydrobid flood is the inverse distance weighted functions and interpolation using a TIN or triangular irregular network. There is another method that is called kriging that is also very useful. We are not going to be doing that in the course, but it's a method that is quite accurate in some situations. Now, the inverse distance weighted method is probably one of the most used methods for interpolating points to a surface. So the idea is that you want to generate a raster information, and then you have a set of points that are located, in this case, in lines like this. So you have, each point has an elevation. Now, the value of, if you want to obtain the elevation at any point here that you may not have the point in between this one here, in the inverse distance weighting, you obtain that as an average of the points that are neighboring the point you want to calculate. And then you weight the values of the points by a parameter p. Then that allows you to obtain points anywhere within this rectangular area, for instance. The problem with that is that the result quality depends on the parameter. If you use, for instance, a weighting parameter of 2, so it's the inverse distance is weighted by the square of the distance, in this case, then you get a set of bumps, as you can see here, which is not very natural for the terrain. Increasing the value may improve somewhat, but you have to keep in mind that this method, although is accurate in some situations, when you have ordered or clustered set of points as you have here, it may lead to some artifacts in the terrain that you get. Now, this is very important because the terrain you get and the terrain that will be eventually interpolated to the mesh is the one that the model will be seeing as the actual terrain. So if you are using this, then maybe you get some flooding that will be a kind of weird due to the incorrect interpolation. In other type of surfaces, this is a surface that has more gradients than the previous one. You can get terrains that are very strange, as you can see here in this, with using p factor or weighting parameter 2 or weighting parameter 10, and you can see the differences in terrain that you get with these two methods. Now, the TIN method, it's very different because what it does is it parts from the same data set, but instead of using an inverse distance weighting, it triangulate the set of points. And this triangulation is used then to interpolate whatever value that lies within the given triangle. It's going to be interpolated linearly within that triangle. So if you had the same data set as we showed before, and then this model will interpolate or will generate a triangular net like you see here, and then each point will be interpolated within each triangle, assuming that you have a linear variation within the triangle. Now, the resulting pattern is much more smoother than in the inverse distance weighting method. And this, I would suggest, is one of the advantages of the triangular irregular network method. Using the same, the second data set that I showed before, this is the triangulation that you get out of this set of points. And you see the terrain here that is much more accurate. It shows the drainage network in much more detail and in much better detail than in the inverse distance weighting method. So just comparing side by side, you see here the inverse distance weighting and the TIN. This is much more accurate in this case. and also the inverse distance weighting and the tin. In this case, this is also much better suited. Now, another method that is used often to build digital elevation model is filling the missing values. So if you have, for instance, a contour map, as you see here, each line corresponds to a given elevation, and you want to fill this, you have tools that you can use to generate the values in between. And this is done by the nearest neighbor method. And it's a method that is always very useful in this case when you want to generate this type of terrain. And I would suggest is another, it's not interpolation, but it's a way to generate digital elevation models. Okay, so that concludes this session, and we'll be happy to answer questions you may have.